My name is Mazeyar Moeini Feizabadi, and my talk is about spatial computing for the masses. So how many of you have heard of spatial computing? Or kind of? Okay, so not too many, and that's because it's not the biggest sector of AI right now. Everyone's really focused on LLMs and trying to get to AGI, but I also think spatial computing is one of the most important aspects for AI. And I'll try to explain that in this talk. So what is spatial computing? Spatial computing merges digital information with the physical world, and it allows us to be in immersive 3D experiences. And it also allows for higher interaction with 3D models, not just 2D images. And as we see very clearly, the trend in LLMs right now is to go multimodal. We have seen, it's actually been one of the biggest improvements to add to any LLM, because it gives more understanding of images, but I also think that 3D images and 3D models will play a crucial role in that. So one of the hardest tasks in spatial computing is self-driving cars from Tesla. And Tesla has a really unique method. They have lots of data and lots of training, so they're able to kind of put everything into a large neural network, and this large neural network learns from videos. But if you're a smaller company, this GIF on the left is from, what's the company in Boston? I forgot. But if you're just one robot in a world that you've never seen before, for example, you're not a Tesla on a car, you need to have an idea of the spatial, you need to have a better idea of your spatial awareness. And you can do this through sensors like LiDAR, but LiDAR is also expensive. So I'll talk about how all the computers are kind of moving away from LiDAR. And this is also Elon's thesis. Elon hates LiDAR, and he refuses to put LiDAR into any of his cars. And he plans to release a full self-driving car in June. So how did we get here? In the 90s, we had SLAM, which is simultaneous localization for automated movement. And it was used for basic robotics. You have a LiDAR on your device, and it spins, and you could localize the robot and make a 3D map. And this gives you a point cloud as seen here. But around 2016, there came this paper called the Colmap paper, and you can see it's actually Rome in the Colosseum. And what they realized is, the intuition is, if you have a bunch of images, you can get the key point from these images, like edge detectors, and from this, you can make highly localized images as well. So you could localize the camera inside the images, inside the 3D world, and you can also get point clouds out of it. And then from Google, there came the NERF paper, which is a neural radiance field for view synthesis, which used an input like this to train a neural network to make a 3D representation, which means the whole scene is inside one little neural network. It's only eight layers long. It's a normal MLP, it's 1.5 megabytes. But maybe not for something this big, but for any object like the size of this room, you could represent the whole room in 1.5 megabytes, because it's super encoded in the neural network. And then there came Gaussian spatting, which is what I focus on, and that allows for real-time rendering. It's a new primitive, it's similar to meshes, but it allows for better aspects, and I'll show you a demo of that. So this is what a format looks like from Colmap. I took this is from the US, and it's a 360 camera, and we walked around the neighborhood. And you can see that all these little red dots are from the 360 camera, and all the points are a point in the 3D world from an edge detector. So we can see we have hyper accurate localization of the cameras. And once you have this, you can feed this into a neural network. So this neural network is super small. But the intuition here is every point, the prediction of a neural network is a point in 3D space. It gives an RGB and an alpha. And then if you sum up the array of this, so it's a volume rendering task, you could get a color out of it. And you measure this color with a ground truth. So it's a normal machine learning task, but we set up the operation differently. So now your neural network is predicting points in a 3D space, which allows you to make 3D models from 2D images. And from the University of Bologna, where I studied, the lab also feeds this neural network as an embedding into a greater llama model. And now you have an embedding of a 3D model which you could feed into a llama model and actually chat with it. It's a very interesting way to get a 3D representation. So here's one. This is from one of my friends, and this is a later model made from NVIDIA. It's called Instant NGP. And you can see the input images that it gives it are very sparse. So it only gives these input images, but if you could localize these, you can make a very accurate 3D model. And when you make this 3D model, it's called view synthesis because you can generate new views. And you can make a continuous view around it. And you can generate synthetic data as well. This is what I did at a company in Bologna. So it's almost like a data generator, and it's also hyper accurate. And I should mention what's different about this from other tasks is you want to overfit this network as much as possible because you have the data, you know what the scene looks like. So it's an overfitting task, which is also very different from other machine learning tasks. And then came out Gaussian spatting. Gaussian spatting is a primitive. It's as if you're using meshes, but imagine a set of 3D Gaussian distributions. You know what a Gaussian distribution is. It's a normal distribution. But imagine these in 3D space. And if you could put these in the right place in 3D, and you have a differentiable algorithm, you could actually make 3D objects, which I will show in this video. So you see all these little dots are actually Gaussian distributions. All the little dots are small Gaussian distributions. And you could train them, and they grow as if they need to grow. And if you have a stable or enough images, you can actually make 3D models like this. And this works much better than meshes. It actually converts, like you cannot do differentiable, meshes are not continuous, but Gaussians are. So you can make 3D models rather easily from a set of 2D images. But it's very difficult. So right now it's kind of a very niche topic. All the papers are like in academia or very difficult to use GitHub applications. But there are a few applications. For example, Reflect is a digital real estate app. I will demo it here. There's iCan.ai from my professor in Bologna, which I internship at. And they make synthetic data from, so for example, you could take a few images of these bars, and then you could make a bunch of synthetic data for training image models. And right now they're working with Leonardo after I left. There's World Labs from Fei-Fei Li, so she's one of the mothers of computer vision. But what she does is she made World Labs for spatial intelligence. So spatial intelligence is after spatial compute, is actually understanding the scene to a really high extent, like predicting the scene. It's a mixture, you could almost imagine adding VLLMs or LLM reasoning and knowledge to a spatial compute scene. And just recently, Palantir, which is a really big American defense, and so it's very controversial, but just recently they opened a role that they require Gaussian spatting for. So you can imagine it's a really fast-growing field. So that brings us to Spatial Graph API. I have around 2 minutes left. How you can use Spatial Graph API? If you want to set this up, you can set it up. It takes like a few days to set it up yourself. But I decided to make an API for it. And you can see here, I have a bunch of 2D images. It's just a banana on the ground. And so previously what I showed was CoLMAP and then the Gaussian spatting pipeline. There are a bunch of different 3D modeling pipelines, but this model just uses CoLMAP and Brush, which is the application one of my friends developed to make a 3D model. So all you have to do is, if you have a file like this, it's just, I call it banana, and I have a folder in there called images. I can run this through a command. It's a normal curl command, a post command. And I feed it the banana.zip, and I call it the API. And what you can see it do is, it's as if it's running on your local machine, but this machine is a Mac Mini hosted at my apartment in Bologna. And it runs the commands exactly like it would if you had the setup yourself, but you don't have to do any setup. And the reason why I'm setting this company up is because this task scales really linearly with the number of GPUs you have. So for example, this is running actually extremely slow, even though it might look fast. It's running on a Mac Mini. But the goal of Spatial Graph is we're going to be training these on clusters of compute rather than just individual computes. So now if you go to talk to any studio that's doing anything with spatial computing, I spoke to one person and he bought 40 490 Ti's in London. But you know, with what we've seen from APIs like the ChatGPT, Claude, and Grok, it's really obvious that you should take all your workload to the cloud. So that's what we're trying to do. And you can see now it's training on my device in Bologna. And if you remember the input, we had a bunch of images like this. It will give you an output. Of course, it doesn't load, you know? Okay, so from these two, the images, you can see we can make a 3D model like this. And the goal is, once we get this on clusters of compute, this will take around a few seconds actually to make something like this. And you can view one other app. It's really popping up in the real estate area, where people are making 3D models of interiors. And we hope to work with these people at Reflect to make their algorithm faster. Because they don't have training. Once you upload, you have to upload your own 3D model, then you can use the viewer. But we hope to beat the training aspect of this. And yeah, so we're also raising our first seed round. If any of you are interested, you could come talk to me. You can find me here. And this is my Twitter and my GitHub, and my email is mazey.moeini@spatialgraph.com. Thank you so much.